Hello YouTube, and welcome back to another episode of Multi-Tech Spec. And today we're going to have a look at trigonometry, Pythagoras, as well as summa triangles. Now, as you can see on the screen, I have a little setup here, and you may be wondering what all these equations are. Well, don't worry, I'll get to them. But first, I just want to say, well, let's start with the Pythagoras, shall we? So this little formula here was invented by a Greek mathematician called Pythagoras, so they say, but I have heard of other stories about another Indian mathematician called Budvayana, and he's been said to have used about 2,000 years before Pythagoras. I read that in a temple, but yeah, I mean, there's loads of speculations about who invented it. I'm not going to say that. I think to say that Pythagoras invented it, I think I may have overstepped the mark there a little bit, so I'm going to take that back. But yeah, Pythagoras, I think, was the first one to the patent office with this idea. So well done, that man. Getting to Switzerland first before everybody else. Well, anyway, the principle behind it is that a squared plus b squared is equal to c squared. So what it's trying to say is that the summation of two sides, right? So any two sides on the actual triangle will be, in effect, equal to the third side. So, well, we can prove this, okay? For the longer side, we can definitely prove this, right? So, say for example, we wanted to do this little bit here. So let's say we wanted to find c. If we had a squared plus b squared, okay, so let's take a as being 6 and b as being 2. Then if we had a squared plus b squared equals c squared, we would end up with... Oh, let's decide to go over there. Oh, we just want to go over there. Okay, well. So what do we say a was? Let's see, a was 2. Let's call it a2. 2 squared. B is 6 squared. And c is just c squared. Okay, now I've actually got this the wrong way around, but right, yes. So we've got 6 squared is the longer side, so that's obviously wrong, because obviously they can never because 6 is the hypotenuse. I've obviously entered this wrong, because a side of a triangle in Pythagoras, right, the hypotenuse is always the longest side. Alright, so there you go. That's a mistake, obviously, so that should be c squared technically, and this should in effect be 6 squared. Okay, because that's the longest side. So the longest side, because we're finding the shorter side, we have to minus it. Okay, now it'll become clear in a minute. Okay, so I was hoping that would go down, but that hasn't. Well, the actual equation comes out like this: 4 plus c squared is equal to 36. Right? So, if you want to find the length of the shorter side, then what we need to do is minus 4 on each side, so you'll end up with and that gives you 0 on that side. C squared is equal to 32. So that gives you... So now, at this stage, in order to cancel the square, we have to apply a root on both sides. So, what is the value of the root? The value of a root is a half. It's anything to the power of half. So, for example, so in this example, it would be c squared. Okay, now I'm going to do it like this, because I think it's easier. To the power a half. Now this, in effect, will equal c. Alright? So, if we apply the same logic to this part of the equation here, we will end up with c to the power 2 to the half is equal to 32 to the power a half. So that gives us c is equal to 32 to the power a half, which will equal to the root of 32, which is 8 times 4. So 8 times 4 to the power 0.5, and in effect that will give us 2. Oh, actually we can break that down even more. I've just noticed. So, equals 2 times 4 times 4. Okay, so that's 8. 8 fours are 32 to the power of half. So that gives us 4 root 2 as the answer. So 4, I don't have a root sign, so I'm going to say 4. I don't have a root sign, so I'm going to call it 4 root 2. 4. Yeah, okay. I suppose I could call it this. 4 to the 2 to the power of half. So that's 4 root 2, pretty much. Yeah, okay. Perhaps I should put another bracket there. That's 4 root 2, pretty much. Okay. So that's how you do for the short side. But what? Suppose you wanted to find the longer side, right? So suppose you wanted to find 6, for example. So you would what you would do is you would add these two sides. So you'd add 2 to c. So let's show you that. So we know that a squared plus b squared is equal to c squared. So let's write that down. Okay, so we know if we call a 2, so let's call a 2, and let's call b 6, for example. No, let's call b the value of c, which we found out to be 4 root 2. Okay, all squared. Just call it root. I should have just done that before. It would have been a lot easier. 4 root 2 all squared is equal to, we'll call 6. We'll call 6 x. Okay, x squared. Then that leaves us with 4 plus 4 root 2 squared, so that's 16. What's 4 root 2 squared? We've just found it out, didn't we? It was 32, I think. Just double check that on the calculator. Bear with me a second. Should be 32. Where's my calculator gone? Oh, right, okay. Check that on the on calculator. 4 root 2 squared. 4 root 2 squared. Take 4 root 2 all squared. Power of 2. Gives us 32. 4 plus 32 is equal to x squared. And as you can see, 36 is equal to x squared. And therefore, root of 36 is equal to 6. So there you go. See, that's how you'd find the hypotenuse in this case. Okay, so 6 in this case is the hypotenuse, and the c side in this case would have been the opposite side, because the adjacent is the angle which is near the right angle. Alright, so it's this little bit here would have been a right angle, which is on this side, because this is two triangles split into one triangle split into two. Okay, so that's Pythagoras really, and that can be applied to any of the sides in this part of the triangle. Now on the other side I have a couple of other tricks for triangles. Alright, and I'll get back to what this means in just a moment. Okay, Sokotoa. But first, let's go down here. Okay, so you might be thinking, what the deuce is all this? What the deuce? Right. Well, basically, these are two similar triangles. Okay? And if you think about it, this is going to be the same as what we're going to learn in trigonometry, which is this part up here. Now I've come down to this part deliberately because I want to point something out to you. Well, in this triangle, okay, we have two parts of information. We have 2 and x, and we have 4 and 24. Notice one is a scale factor of another. Okay, 4 and 24. Now if we divide 24 into 4, okay, then if we divide 24 into 4, we notice we get a scale factor equal to 6. Alright? Now it will become clear why this is significant when we reach trigonometry. At the moment, just bear with it. So we have a scale factor of 6. Now notice that one of the sides must therefore be 6 times bigger than the other. Hence the 24. Now, 2 to the x, we could assume that x is going to be so then therefore we can assume that x is going to be 6 times bigger than 2. So if we equate that, so if we equate these two bits, we should end up with a little answer. So I'm just going to try and get the fractions out here to make you see a bit clearly. Let's try... Oh, okay. Let's go to equation mode. And let's do some fractions. Is equal to that. Then we should have 2 over x. Okay? So if we say 2 over x, for example, okay, we'll treat it as a scale factor, is equal to 4 over 24. And if you rearrange this, we end up with 4x is equal to 48. 4x is equal to 48. Therefore, x must be equal to 12. Okay? Because if you equate these two values of the actual triangle, 2 to the x and 4 to the 24, then, and notice that the scale factor is 6, then you should be able to appreciate x being 12. Okay? Because it's 6 times bigger than 2. So as you can see, a ratio is being formed. Okay? So therefore, if we have a value of y, okay, we know that that value of y will be 6 times bigger than the value of this total length here. Okay? But at this point, we can't find this little length here. But we know that the value of y will be 6 times bigger than whatever we find down here. And that brings me up to date with trig. So if we can appreciate all that, then it shouldn't be any problem for us to understand these little trig ratios that we have here. Okay, so you have sine is equal to opposite over hypotenuse. Now the hypotenuse is the longest side. The opposite side is the side which is opposite the angle. So in this case, that would be C. The hypotenuse in this case, you could take it from either side as being 6 or D, because it's always the longest side, okay, in a right angle triangle. You can have other types of triangles which are drawn, but typically you would do trigonometry with something similar to a right angle triangle. But then when you go up to higher level maths, you can obviously have different ways of representing this, and different identities, different formulas to signify this for different purposes, obviously. Okay, so the adjacent side is the side which the angle is adjacent to the right angle. Okay, so it's the side where the right angle resides, if you will. Okay, and those explain these little formulas here. So now that we found C on this triangle here, all right, and even without C you can find the angle. What do you propose the angle will be? Okay, what do you think the angle will be? Well, if we look at this, we will notice that we have the hypotenuse and we have the adjacent. So what type of formula will that cover? Oh, okay, yeah. You have the hypotenuse and the adjacent. So we got TOA, T-A, okay. Oh, right, I've written the cosine formula again. Okay, so just let me correct this. Is equal to opposite over the adjacent side. Right, okay. So you will notice that it's the cosine formula that we need to use. It's the cosine. So, if we know that, then let's try it, shall we? So we'll say, just make another text box around it. Insert text box. Okay, so then we could say cosine is equal to the adjacent over hypotenuse. So we know that the adjacent side is 2, and we know that the hypotenuse side is 6. Okay, we'll call this theta. Okay, we'll just insert the theta in here. or x is even better still. That would be better. Cosine x. Then we could say cosine x a third is equal to a third. Okay. Then we could take cosine to the other side. So we could say x is equal to cosine minus the power of minus 1 over a third. Okay. So just all we've done is taken cosine over to the other side. Okay. Which we can do. Because cosine minus 1 is the same as saying tan inverse or cosine inverse or sine inverse. All you're doing is you're doing the inverse of the function that you were previously having. So effectively you're doing the reverse. I think I've got that right. I would say you're doing the inverse operation. Okay? So that is to say you are doing the opposite operation. Yeah. Okay, so you have that. So then x in this case would be equal to an angle. Okay, now the angle that you'd usually have in here would have to be less than 1 typically. See, because you will get a math error for anything that's bigger than 1. It has to be 1. So you will know if you've made a mistake if the two angles here, right, simplify to become anything above 1. Okay, because it's wrong. You can't when you draw the graphs, okay, from 0 to 360, and let me just find one for you here. Okay, so that's a really good sine graph, right? Courtesy of Google, from wsd.org. Okay, just calculus, right? And you will notice that the graph is like that. Okay, from 1 to 1, unless you're doing some kind of operation to the graph, but you will notice that it always goes to 1. It never goes beyond 1 by default. Something has to happen. For example, a stretch, okay, to a maximum point of 2, for example. Okay, something has to happen, and it's the same with the cosine graph. Okay, let me just show you. Okay, so you have 1. See, this is in radians, but it's the same thing. Okay, so it's going to 1 and minus 1. Same thing, cosine graph. Tangent graph. Okay? Me. Right, but it goes to 2. So, am I wrong? Ooh, I'm wrong for the tan one. Ooh, interesting. Am I wrong for the tan one? Ooh, I am wrong for the tan one. Oh, that's interesting. I like that. Well, for the tan one, it appears you can go as high as you like. And the reason for that is because of this asymptote here. This is called an asymptote. The reason for it being called an asymptote is because this line here, goes close to this asymptotic line. So asymptote really is like a line that doesn't really exist, but the line goes close to it, okay? In layman's terms. So this little line here goes like close to it, but never really touches it. And that's why it's wrong for the tan one. What I've just said for the tan, alright, that you can't have a number of 1 bigger than for tan is wrong. Okay, and that's the reason why. Okay, so there you go. See, I learned something new today as well. Okay, so I hope you've learned something today. It's my little rant on about trigonometry and Pythagoras. You can do other things as well, like look into identities, but I think I'll touch up on that in another video. Thanks for watching. This is Multi-Tech and I hope you learned something today. We will be continuing back on with scheduled computer stuff, Linux and Windows and what have you. As soon as I've got a little bit of time left, I'll do that. But at the moment, like it's a bit difficult because I'm in another location. I'm not in my default lab, which is down in London. I'm no longer in London. But never mind. I'll get back onto it and find it, and I'll show you the kind of stuff that we've been doing from before. So like you know the remote desktop thing. I'll show you what that kind of looks like and how fast the WAN link is that we've created. So yeah, stay tuned. More to come. And yeah, I hope you've enjoyed this video, and you know, it feels good to be back on YouTube for once after a couple of months. So yeah, okay, cool. Some more to text back. See you soon.